Hey Geometry, we're going to talk about dilations a little bit more and how they map angles. And just remember, when I talk about mapping, I'm not talking about driving from Arkansas to Missouri, okay? We're talking about when we have transformations of things. So first of all, how do dilations map triangles? So we're going to go through like 4 separate questions, sort of get us into the right mindset. We're going to talk about how we map triangles with an example, how we map rectangles, squares, and regular polygons. So yeah, we're just getting the juices flowing and reminding ourselves how things work. So first of all, let's make a conjecture. A conjecture, if you remember, is just a guess. So I'm going to write down an answer, and you guys are going to think about it for a second. Okay, so how do dilations map triangles? A dilation maps a triangle to a triangle with same angles, and all of the sides of the image triangle are proportional to the sides of the original triangle. I didn't save myself enough room there. If you remember, the image is what happens after the dilation, and then you have the original or the pre-image. We have 2 triangles here. If we look at these 2 triangles, I can check the sides of the triangles with the image and the pre-image. It looks like I went bigger, so I'm going to put the larger number over the smaller number, and let's see what my proportions are. Looks like that one's 2. Let's check the next one. That's also 2. That's good. Check that last one. That's also 2. And all I did was put this number over that one, etc. Okay, so to verify my conjecture, I drew 2 triangles and I checked I measured the sides, and then I checked that the proportions were correct by dividing the image by the pre-image, okay, or the original. I failed to point out, so these are all the sides that are proportional. If we talked about the angles, get our protractor out, the angles are congruent. The angle measurements did not change for both the image and the original. So the angles map to angles of equal measure. Okay, all the angles in the original triangle are dilated to angles that are the exact same measurement to the corresponding angle in the dilated triangle. So angle A is congruent to A prime, right? Triangle C is congruent to triangle C prime. That should be a congruent symbol. It didn't come out. There we go. We'll just say the measure of angle A is equal to the measure of angle A prime. The measure of angle B is equal to the measure of angle B prime, etc. Okay, so how do dilations map rectangles? Make a conjecture. So think about it. Okay, you think about it for a second. I'll write down the answer. So if you look at a rectangle, if you dilate it, so what we've done here is I've got my center of dilation. I came out. I did go smaller. Here's the pre-image and the image. A dilation maps a rectangle to a rectangle so that the ratio of length to width is the same. So let's go ahead and test it. I copied 2 from my book onto here so I didn't have to try to draw accurately. If we look at the large rectangle, I have length to width. I'm going a ratio of 3 to 2. Okay, here I have length to width. I have 1.5 to 1, which I don't really like fractions or decimals when I'm looking at ratios. So if I double both sides of this, I'm going to have 3 to 2. My ratio of length to width, the original one has a ratio of 3 to 2. The dilated one is 1.5 to 1, which is the same as 3 to 2. So the values of the ratios are equal. My length to width is equal. And since angles map to angles of equal measure, so angles are equal, we just did that in the last example. We actually don't have to talk about it again. Angles map to angles of equal measure. So all the right angles in the original rectangle are dilated to right angles in the new rectangle. Did I say triangle? They're both rectangles. Okay, how do dilations map squares? I bet we'll see in a second. Think about it. I'm going to write down the answer. Be right back. So for a square, a dilation maps a square with side length L. I drew original square and then a dilated square. So if we have a square with side length of L, which over here it's 2, it dilates to a square with side length R times L. R would be your scale factor, right? R equals, oops, not sale factor, scale factor. What else can I tell you? So if I have each segment of length L, so here AD is mapped to a segment of length R times L. Here we have A prime D prime. Looks like my scale factor in this case is in fact 3, because 2 times 3 is 6. We know that the angles are equal. The angles do not change in dilation, so we're good there. So the dilation maps a square with side length L to a square with side length R times L. That's really, squares are easy. Gotta love them. How about regular polygons? If you remember, the word regular means all the sides of the polygon and angles of the polygon are equal, are the same. Okay, that's what regular means. Okay, so how about conjecture? Be right back. So just like everything else, and very similar to the square, polygon with a side measurement of L gets mapped to a polygon with a side length of R times L, and the angles are equal. We'll verify the conjecture by looking at diagrams on the next slide, because I couldn't fit it quite well on this slide. If we look, okay, we went from polygon A, B, C, D, E to polygon A prime through E prime. The length of my sides, I went from 3 to 12. So it looks like my scale factor is 4. All of the sides, all of the lengths are equal to the scale factor times the length. So each length of this regular polygon is 3, each side length of this regular polygon is 12, which is 4 times 3. And if we measure the angles, the angle measurements are all equal. Alright, so let's talk about this for a little bit. First of all, we went into detail with 4 examples. In each example, the sides were all proportional. And we had ones that were proportional. Length times width were a perfect ratio. The ratio was held. And we had the lengths of the squares and the regular polygons equal to the scale factor times the lengths. And most importantly, all angle measurements held equal. Guess I could say remained congruent. That's what we just looked at in our 4 examples. If I take it just a little bit further, next slide. In Algebra 1, when you first looked at dilations, you looked at them on coordinate grids. So if we look at a dilation here, we showed back in Algebra 1 that a dilation with a center, here we had a center at the origin, which would have been down here, right there. There's my center at the origin. A dilation with a center at the origin and a scale factor of R, an angle formed by the union of the 2 rays and the image of the angle were equal. Now you remember the definition of an angle is the union of two rays. So I have two rays there and two rays here. The union of the two rays forms an angle. Excuse me. So if we look at these two angles and their scaled sides, the angles actually remain equal. Q and Q prime are congruent. The important part that I want to point out right now is that line QR and Q prime R prime are parallel. See if I can highlight that a little bit. Oh, that's huge. Sorry. Let's try that again. So these two lines are parallel and in fact cut by a transversal. So this angle and this angle are congruent. Okay, and we can also say that these two lines are parallel and cut by a transversal, therefore these two angles are congruent. And by substitution, we can say that, if these two angles are congruent, then these two angles are congruent, then those two angles are congruent, right? Okay, so taking that to the next step, let's look at our next exercise. Recall what you learned about parallel lines cut by a transversal, specifically about the angles that are formed. Okay, basically what we learned was when parallel lines are cut, that's the word by a transversal, then the corresponding, angles are equal in measure. We learned that a long time ago, right? Also, alternate interior, that should be an R. Alternate interior angles are equal in measure. And then finally, alternate exterior. Are equal in measure. We're really stretching back, but this is stuff we all have learned. Okay, a dilation from center O by a scale factor of R maps angle BAC onto angle B prime A prime C prime. Okay, if you remember a few slides back, this is what I just showed you on the coordinate plane, but we don't have a coordinate plane. Okay, so by properties of dilations, we know that a dilation maps a line to itself. So I mapped line AB onto line A prime B prime. And we also know that these two lines are in fact parallel. And these two lines are parallel, correct? Okay, we learned that with just the properties of dilations. So here I have two lines that are parallel and a transversal. So here we have D is our point of intersection. So I've marked everything over there. I've got parallel lines. I have a point of intersection, and I've got corresponding angles that are all congruent, right? And by substitution or the transitive property, it makes them all congruent. So the dilation maps angles to angles of equal measure. Okay, we showed it really well on the coordinate plane also. So to wrap this up, we're going to discuss a few other options briefly. First of all, the dilation theorem for angles is as follows. A dilation from center O and a scale factor of r maps an angle to an angle of equal measure. We proved that using parallel lines and transversals. But there's other instances that we really need to discuss just briefly. If I have, angles that maybe dilate out, where the sides of my angles, they're rays, so rays extend out forever, but maybe the points on the rays have gotten shorter, where I've got A and A prime. Our angles are still equal measure. It doesn't matter, right? I could draw an auxiliary line and show that I have equal angles. I know, because I just drew parallel lines. Correct? How about if we draw some angles like this, and I just extended it out where I've got all of my points, A and A prime, but we still have parallel lines and corresponding angles. One more. If I draw some triangles, please excuse my inability to draw triangles well. I'm going to draw that just a little bit better, a little bit bigger, so I can mess with it. If I drew some triangles and I want to break this up into pieces, okay, let's just pretend that I am scaling this, dilating it. Okay, I dilated the square so that the two vertices lie on the other two sides. Okay, so I've got a triangle, I drew a square inside of it, and I drew a ray through the vertex of the square that doesn't touch the side of the triangle. So A, C, B, this is my ray. This point T can be used as one of the vertices of the dilated square, correct? And I can, if I had my set square, I could awesomely draw all these parallel lines and show that my new square is scaled, okay? 3 of the 4 vertices on the square are on 2 sides of the triangle. The location of the 4th vertex must be on side BC. Since the ray was drawn through the vertex of the small square, let me change that color. Through the vertex of the small square, a scale factor R maps the dilated vertex on the ray. So by constructing that ray from vertex A through the side of the square that isn't touching the triangle, we can easily construct a square that is a scaled square, the first one, whose sides touch the other sides of the triangle. So since the dilation maps squares to squares, it's just a matter of locating the point of the vertex along the opposite side of angle A and then constructing the square. Okay, that's it. Our lesson summary: dilations map angles to angles of equal measure. Dilations map polygonal figures to polygonal figures whose angles are equal in measure to the corresponding angles of the original figures, and whose side lengths are equal to the corresponding side lengths multiplied by the scale factor. Okay, sort of an easy lesson. We'll see you at the problem set tomorrow.